Welcome guys. So in this tutorial, in this amazing video lecture, I'll be doing a lecture series on quantum mechanics. So my first concept is to do a syllabi introduction to this paper. So I will go deeply and explain maybe the things I'll be doing. So you see, quantum mechanics is an abstract knowledge, an abstract thing it's to the edge of human knowledge. You see, physics is the study of matter, energy, and its relation to the universe, okay, from the galactic to the intergalactic world. So you see, physics existed earlier on in earlier years, okay? But if you ask maybe what's the most fascinating branch of physics to study, I'll simply say it's quantum mechanics. So with a great honor and responsibility, I want to do an introduction video to quantum mechanics and then give you the approaches and the syllabi that I'll be using to teach quantum mechanics. So we are saying quantum mechanics is the study of matter and energy to the smallest of scales, the scales of atomic and subatomic particles. So you see, in the real life, in the real world life, you see, human brain is more conversant with the classical world, okay? So you see, in quantum physics, we see the universe in the most smallest of scales. So you see, having this knowledge is very crucial in the real day-to-day life. So we are saying in this video, I'll do a syllabi introduction where I'll split the syllabi into 3 parts, okay? The quantum mechanics 1, which is a beginner. So this is a beginner. Fresh from high school, where we'll see the problems on origin of quantum mechanics, black body radiation, photoelectric effect, Compton scattering effect, pair production, the Broglie hypothesis, Davison gamma experiment. We'll do two-slit electron interference experiment. We'll do wave particle duality. We will do wave packets. We'll do group and phase velocities. We'll do Heisenberg uncertainty principle. We'll do the Gaussian wave packets and uncertainty relations. We'll do atomic structure and spectroscopy and lasers. Okay, so that's beginner quantum mechanics. But now, after us advancing those topics, after us being conversant with all those topics, we'll proceed and do the second branch, which is mechanics 2, of which these are designed for undergraduate students. This is for intermediate students, okay? So here we will see the concepts on, I'll introduce firstly quantum mechanics in both approaches, okay? You see, quantum mechanics has 2 formulations. We have the formulation by Schrödinger, which is Schrödinger wave mechanics, and also we have the formulation by Heisenberg, which is Werner Heisenberg, which is the matrix mechanics. So in this lecture that we'll be doing, we will see both formulations of quantum mechanics to this point. So my first step, I'll do wave mechanics by Schrödinger. So that's my first formulation. That's what we'll be dealing with. Then we're saying in these we'll do the Schrödinger wave equation, we'll do the wave function and probabilistic interpretation, we'll do normalization, we'll do expectation values and operators, we'll do ties, we'll do stationary states, we'll do probability current, we'll do free particle, and then we will use the Schrödinger wave equation to solve infinite square well potential, delta function potential. We'll do finite square wave potential, step potential, and then we'll do the hydrogen atom. And again, maybe just to say and mention, we are saying before you advance your knowledge to quantum mechanics, simply you must understand the basics of calculus, ordinary differential equations, partial differential equations. You'll have to understand linear vector spaces, linear algebra, both levels of linear algebra for you to be conversant with quantum mechanics. Then after clearing that, after clearing wave mechanics, we will do matrix mechanics by Heisenberg, where we'll do linear vector spaces, Hilbert space, Dirac notation, and operators. We'll do observables. We'll do matrix formulation. Okay. So in this matrix formulation of quantum mechanics, we will use it to solve so many concepts. For example, the harmonic oscillator, the angular momentum, and so much more. Then, clearing with that, both formulations, we will go down to quantum mechanics. This is now for the advanced students who are in their later years of undergrad program, or the postgraduates, the earlier years. So we are saying in this section, we'll be dealing with the spin, we'll deal with the Stern-Gerlach experiment, we'll deal with identical particles, we'll deal with the exclusion principle, the Pauli exclusion principle, we'll deal with the time-independent and dependent perturbation theory, we'll deal with the variational principles, we'll deal with the WKV approximation, we'll do with the Zeeman effect, we'll do spin-orbit interaction, addition of angular momentum, we'll do scattering and relativistic quantum mechanics. And then after clearing all those, we are saying we need to understand quantum mechanics today. I'll say, like, quantum mechanics is very vast. Okay, so after clearing all those topics, maybe I'll do another video, okay, just to show the philosophy. Okay, we'll do the philosophy of quantum mechanics. Okay, the spelling is not coming. So we'll do the philosophy of quantum mechanics, where we'll do the EPR paradox, we'll do quantum untunneling, we will do the Bell's theorem. So after us having that, going down to the philosophy of quantum mechanics, then we'll be able to clear all these concepts. Now, after us introducing this syllabi, we are saying just maybe an engagement. We are saying in quantum mechanics, it has its own problems. Okay, so the first problem is conceptual understanding of these concepts. You see, I'll take you back and tell you we have conceptual difficulties or understanding in this essence of the human brain is conversant with the classical physics, the classical world, but now we are diving into the quantum world. So you see the transition, it's not likely to take place in the normal human mind. So it has more conceptual understanding, where in this conceptual understanding we'll do the concepts on quantum untunneling. Okay, we'll do quantum entanglement, and so much more. We will do wave-particle duality, of which my next video I'll be introducing the singular nature of light. Then now comes in conceptual understanding, where we're saying now light is a wave and a particle. That's wave-particle duality. We will do probabilistic interpretation and so much more. Then we're saying in quantum mechanics it has a mathematical complexity, so you must understand fully the basics of calculus, physics, math, and so much more. So it requires concrete and heavy math formulas and skills to solve most of the problems in quantum mechanics. Then we're saying it lacks concrete examples. So you see, quantum mechanics, you can't really borrow the ideas from classical physics to the quantum world, you see. So it lacks concrete ideas, examples. So those are the problems and challenges for those who will be taking this paper. But it's a fascinating and a very, very successful theory so far. And basically we are saying quantum mechanics is the study of matter and energy to the smallest of scales. So you see, it means quantum mechanics lays a very vast background in most of the fields, most of every other field in this universe. You see, it lays background to chemistry, it lays background to biology, medical imaging, it lays background to nuclear physics, lays background to particle physics, and so much more. So you see, this paper is so much important, okay, because it's the bedrock of how the universe operates, okay. So after that, we are saying that's all we'll be having. So we'll do this. My next video I'll introduce what's light and continue. So the way I've structured to teach quantum mechanics is normally most people teach quantum mechanics by just applying the principles of quantum mechanics, taking the principles of quantum mechanics and then applying them to the systems that the problems are being evaluated. But for this case, we will do quantum mechanics in a very different approach, where we are saying we will do the historical developments of quantum mechanics, okay? So quantum mechanics has evolved over decades of years, possibly from 1887 to about 1937. So we will do the historical developments of all these concepts, then engage in the mathematical world of it, then we'll summarize and evaluate our knowledge to this paper. So we are saying quantum mechanics is a hard paper. That is, if I'm introducing it honestly, this is a hard paper, so it needs more dedication and time. And usually say don't worry, because you're not the first person to use this paper. So great minds, for example, Niels Bohr, we have Richard Feynman. So Richard Feynman quoted this and said, if you think you understand quantum mechanics, then you're not, okay? And then Richard Feynman said, if you haven't been confused by quantum mechanics, then you don't really understand it. So you see, we have so great, very many great minds that have faced quantum mechanics and successfully said it's not an easy paper, okay? So it's not an easy paper, it needs more work and dedication. So I'll be uploading the videos, almost 2 videos weekly, and I'll be doing this playlist for the coming months and maybe years to come. So please like, share, subscribe to my channel, follow for more concept and intuitive explanation to the human knowledge, the best of the human knowledge we have.